All right, and we're back for the second hour here on Friday, June 26th, part 2 for 17. We'll be finishing chapter 17 here. So yes, homework 2 is due tonight for that. And what you see up on the board here is CHEM352 again. We've got the molecular orbitals of benzene, and I've got it spinning right now, or I can grab it with my mouse. And this is the lowest energy filled molecular orbital right here. And you see there's 6 total molecular orbitals. And why is that? Because there's 6 atomic p orbitals that are added here. Now that it's a ring type structure, so there's a couple that are the same energy here. These 2 are degenerate orbitals, we say. They're 2 different ways of having one node in the molecule. Remember, a node goes through the molecule. Let's see if we can visualize that one. Yep, there's that one right there. You can see a node. Let me turn spin off. You can see a node right here, okay, which is one way through the atoms to create that next orbital up. And then this molecular orbital right here goes through the bonds, and that's also one node. So quantum mechanics says those are the same energies, okay, even though they're actually made a little bit differently. And then if we go up to the next higher energy ones, sorry, it's the Wicker view here for the orbitals, but you see there's a node here and a node right here. So that's 2 nodes, and here's also 2 nodes right through there, one there and one there. Those are anti-bonding orbitals, and then the highest anti-bonding orbital is right here with 3 nodes arrayed there. And again, it's because of the cyclic structure, you've got some symmetry there, so the nodes can go through atoms or bonds. But the important one is this one right here, okay? You see the donut structure, and that's electron density on the top and the bottom. And what does the shading mean again? Make sure you remember what that is. Does it mean red and green? High electron density, low electron density, kind of. That's the mathematical prefix on the wave equation, okay? So it has to do whether the probability is high or the probability is low where the electrons are found. So it's actually the sign of the wave equation that oscillates. These have wave-like properties where the electrons are, but the 2 electrons in the ground state oscillate like that, in phase with each other. The next 2 electrons are oscillating like this across with a node in the atoms, okay? Those are 2 electrons there. And then 2 electrons here oscillating in this manner across, what, the middle of the bonds, like that. So 6 total electrons in the ground state, and they're oscillating a little bit differently, but in such a way that you maintain the overlap. But it's different than just how we draw the structure, okay? So I like to show that. Again, that's on ChemTube 3D. You can go to that with any device you have under structure and bonding. And I think it's found here under molecular orbitals, benzene. That's what we're looking at. But you can look at a number of other ones here and manipulate it with your mouse. To see the different orbitals, you have to click on this diagram here. Okay, see where I'm clicking there with my mouse to see that then, and then you can inspect that you can see the structure there. All right, let's define precisely what aromaticity means, okay? What do we mean when we say aromaticity? Well, there's some criteria here that we have to have in order for a molecule to benefit from this extra 30 kcals per mole energy stabilization. Benzene's the archetypical structure, but there's many other structures that kind of look like benzene, but not really. So you need to be able to apply the criteria in a strategic way here. The first thing is cyclic array of pi electrons, okay? So the hybridization has to be what? sp2 hybridization, okay? We can have sp hybridization intervening, but the ones that are continuous and cyclic here all have to be conjugated, okay? So that's a key thing here. But the orbitals that these pi electrons come from are p atomic orbitals, okay? You already have a feel for that from alkenes, right? And the next thing here, it has to be planar. That has to maximize the overlap, it has to be flat, okay? So the framework, benzene, we've talked about that being all flat there, all 12 atoms are all flat there. And then the other criteria here is 4n plus 2 is the number of those pi electrons, okay? 4n plus 2, where n is any integer, n can be 0 on up, and then it's a mathematical progression, okay? So you guys like mathematical progressions? This is one of the really neat ones found in nature. Nature likes certain numbers, okay? You need to get used to that, especially in chemistry, right? We have the octet rule. Why the octet rule? You know, 8 electrons arrayed around that central positively charged atom. Well, that's just the efficient number at that size, that shape that you can pack around that charged nucleus for that size frame. And we got a similar magic number here. But the numbers, what? 0, if we put 0 in there, then what? This equals 2, okay? If it's 0 there for that integer. So 2 pi electrons, if it's flat, continuous, yeah, that can be aromatic. If it's 1 here, what is that? That's 6. And that's benzene, the 6 pi electrons. Like I said, benzene's not the only one. What if the integer is 2 here? What's that? Well, that's 10, right? And then on up, 14. 18, 22, on whatever. Notice here, if it's 4, what's up with that? Well, that becomes anti-aromatic. And whoa, why is that? Well, we got to look at the MO diagrams to see. You got to have a feel for it looking at the chem tube array there, but we'll define that a little more carefully. And what about 8? How come 8 isn't represented there? What's wrong with 4 and 8? Okay, well, it doesn't fit the Huckel rule, but it's how it fills those molecular orbitals, okay? You got the lowest one and then the 2 degenerate ones with 1 node each for benzene. You see that adds up to what? 6 pi electrons, not 4. 4 would be having that level half filled. Actually, that's diradical character, and it's actually less stabilizing when you half fill that at that position. We'll look at the frost circles to define that. But these are the ones that have stability, 2, 6, 10, 14, 8, 22. The other thing we can use to define aromaticity here is when the aromatic hydrogens on the periphery in the Proton Nmr are what? Shifted downfield to what? 7 to 8 ppm. Okay, that's another way to tell whether the thing's aromatic or not. There's kind of some ambiguity how flat things can be. We'll have them be perfectly flat. We'll show you some examples where they can't quite get flat, but they still have maybe 6 or 10 or 14 electrons, but they're non-aromatic then, okay? Anti-aromatic if it's 4 or 8 and constrained to be flat, okay? And we'll point those out, those stabilities that are there. Another thing that you can see here is different reactivity, okay? Different types of reactions, and I already showed you that with benzene, how it brominates. So when we have different reactivity, that might be a hallmark of aromaticity as well. But with these other criteria here, we can nail that down. So in order to get this extra stability, we have to see those criteria there. All right, let's look at some examples, see if we can figure this out. So we've got, how about this one? And how about this one? So what are we going to call these? This is Cyclo Butadiene, and this is Cyclooctadiene, stop signine. What about these? Well, they could be flat. Their pi electrons are certainly conjugated, but what about the number of pi electrons? How many here? 1, 2, 3, 4. Uh-oh, 4 electrons, okay. And if you look at it sideways here, it indeed is flat. You can kind of pucker it a little bit to try to avoid being flat here, but being flat here and having these constrained with 4 pi electrons, it turns out to be anti-aromatic. And I'll give you a little more data here. This is kind of an interesting compound. This compound itself has never been made before on its own. A lot of people have tried to make cyclobutadiene, but it's so high in energy and so difficult to isolate. It's been made fleetingly and isolated in a low temperature matrix, solid state, but it's never been made on its own and put in a bottle. But there is one that has been made. It's this guy. tetratertbutyl cyclobutadiene. That's been made. And the X-ray structure has actually been taken of this. It is a high energy molecule. It's hard to make. But having these 4 tert-butyl groups kind of helps stabilize this. And the X-ray data is really kind of neat. It shows that this bond right here is indeed a double bond, 1.38 angstroms. And in the X-ray, this bond here, which turns out to be a true single bond, turns out to be 1.51 angstrom. And I think that's amazing stuff, and that's indicative of what? These 4 pi electrons in a flat structure turns out to be anti-aromatic. And it has true double bond, single bond character, okay? So again, anti-aromatic here because it violates that Huckel rule, okay? And it has to be flat because it's a small ring. Let's look at this guy, Cyclooctadiene. So how many pi electrons do we have here? 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons. So if that were flat, it would be anti-aromatic. But this structure is well known. This is a stable compound. It can be made a number of different ways because it's a bigger ring, actually. But is it flat? No. It turns out it's tub-shaped. It's kind of hard to draw. Let me draw it. Oh, there I go. Look at that. Pretty high quality artwork here for a Friday, don't you think? It's tub-shaped, okay? And this tub shape, you can take an X-ray structure of this, and let's see. It turns out these double bonds right here are 1.33 angstroms, and these single bonds here are distinct 1.49 angstroms, okay? And it's puckered out of plane. These are not conjugated now. If you draw these orbitals here, you'll see that they're not conjugated to each other. You can make a model of that and see. But what do we call this? We don't call this anti-aromatic now because it is puckered, it's out of plane, whatever. So instead of being flat and super high in energy and unstable, this one is stable, it can be made, but it's more like what? Isolated dienes. So what are we going to call this? We're going to call this non-aromatic, okay? One other thing here, let's see. I thought I had the NMR of this too. Oh, okay. So yeah, you can look at the NMR. All these hydrogens are all the same. So the proton NMR, where do you think those show up? Benzene, those hydrogens show up at 7.3 ppm. Where do you think these show up in cyclooctadiene? Yeah, in the normal alkene range. Let's see. I had the number. Where is it? Oh, 5.8 ppm. Okay. So yeah, that's outside of the aromatic range. That's shifted further upfield. Okay, so it's a typical alkene, non-aromatic because it's not flat. So those are a couple of good ones I think to keep in mind. Yeah, there's a question from Aaron. Very good.
Dr.
Yes.
How can we tell if a structure is going to be puckered or not based on how it's drawn?
Yeah. Yeah. So this one you kind of have to know about it. And this 8-membered ring, to flatten that, these bond angles internally here are like 150 or so. So that's inducing some strain to try to flatten this. And then if you look at the actual X-ray structure, okay, so you have to have some extra data there. Actually, anti-aromatic are pretty rare. These are these smaller ones that are constrained to be flat. If they have the wrong number of pi electrons, they'll almost always be non-planar and puckered out of plane. But you have to get a feel for it and work a couple problems that way. Does that answer your question, Aaron? Kind of an empirical.
Can we assume they are flat unless we have extra data?
Yes, yes. And the extra data might be NMR data or X-ray data. But counting the number of pi electrons is the first thing when we look at these problems, okay? If we've got the 4n+2 rule going on. And that's what we'll look at. That's a good segue into these next couple of topics, Aaron, so thank you. Let's see. How about this one? Is this one aromatic? Cycloheptatriene, we'd call that. Hepta, so we got 7 there. Is that aromatic? We got 1, 2, 3, 4, 5, 6 pi electrons. That looks good. That's 6. Fits the 4n+2 rule, where n equals 1, like benzene. But is this a continuous array of pi p atomic orbitals? No. Here you have a CH2 group, okay? Add in all the hydrogens there. Maybe you didn't see that before. So what would we call that? We call that non-aromatic. And the NMR bears that out. Those show up at around 5.5 ppm for that. Let's look at this one. If we have the same 7-membered ring, well, let's put a cation there. So add in all the hydrogens now. We've got hydrogens all around there. Instead of having 2 now, because we got the cation there, this is cycloheptatriene cation. It has a special name. This is called tropylium cation. And it's known. You can make it and put it in a bottle. Okay. In fact, you make it from the cycloheptatriene and you react it with triphenyl methyl cation or trityl cation. And this will actually pull off a hydride and make the tropylium cation. Why? Because tropylium cation is aromatic, right? It's got how many pi electrons? 1, 2, 3, 4, 5, 6 pi electrons. It's flat if you take an X-ray structure of this molecule, and you can do resonance structures of this, right? You can push this cation here, 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 and it alternates all around the ring. And we can often draw tropylium cation like this. And also in the NMR, where do you think the NMR, these protons show up? Yeah, 7.1 ppm. Very close to benzene, definitely in the aromatic range. So tropylium cation. So the Huckel rule, the criteria we looked at, has nothing to do with charge. It has everything to do with being flat, cyclic, continuous, conjugated, and the right number of pi electrons. So yeah, that one's fine. Let's look at another one here. How about a 5-membered ring? How about Cyclopentadienyl? Is that aromatic? No, we have the intervening methylene, sp3 hybridized. Remember, it's got to be cyclic continuous sp2 hybridization. So this one we would call what? Non-aromatic. And indeed, Proton Nmr, these are in the 5 range. Okay. Can we form something that's aromatic though? How about this? Cation. Tropylium cation was the aromatic one before. How about cyclopentadienyl cation? Is that one aromatic? No. How many pi electrons do we have? 1, 2, 3, 4. And yeah, hydrogen here, here, and here. We can draw resonance structures of this. We could say, oh, this must be stable. This must be happy here. But no, it's 4 pi electrons. And it is flattened like this. It will try to get out of plane here. But if this molecule is what you're talking about here, this is flat. So what is it going to be? Anti-aromatic. Okay. It's very unstable and it's very hard to make. It has been made and studied theoretically, and it's 30 to 40 kcals per mole higher in energy. Okay. So this is the anti-aromatic. Well, let's see. Is there a charged one we can make from this? What would we have to do? Not taking off a hydride, we'd have to take off what? A proton. And you can actually use base to do this. T-butoxide, in fact, can do this. And you can leave behind the pair of electrons and form this, Cyclopentadienyl Anion, or CP, this is sometimes called. CP anion is very stable, and it can be easily made, even using hydroxide, okay? Which means what? This is taking a proton off a carbon-hydrogen bond here. This here, pKa-wise, must be pretty low, right? The pKa of tert-butyl oxy, the alcohol there, is what, about 18? So what is this? The pKa here turns out to be 16, which is amazingly low. It's quite acidic. You can have a pretty good base. It doesn't have to be a super strong base like LDA or butyllithium. It can be hydroxide or T-butoxide. Can take that proton off, leave behind the anion. Why? Well, CP anion what? Has 6 pi electrons. Okay. And there they are. It's flat. It's isoelectronic with benzene. We can look at the structure and draw resonance structures of it, or we can just say this, the donut here with a anion in the middle. And what does it look like? Let's look at it kind of sideways here. It would look like this. where you've got what? 6 electrons in there, right? And that will give it an anion charge. And look, they're all, here'd be the low energy one, okay? And that fits the criteria for the Huckel rule. So CP is a very good anion. It can be easily made. All right, we're looking at these small rings, and hopefully that's giving you a feel for that. Throwing on a little reactivity also. How about this guy? It's a funny looking one, isn't it? Cyclo Propene, we'd call that. Is that aromatic? No. We have CH2 right here. Let's see, what about the cation of that? Could we form the cation? Yeah, we could react that with trityl cation and pull a hydride off. And guess what? That compound right there, cyclopropenyl cation, is aromatic. Okay. Why? Because it's got 2 pi electrons. And yes, it's flat, continuous, all there. Okay, so all these p atomic orbitals are up there, completely planar, and those 2 pi electrons, it's charged, okay? And we can draw it like this if we want to, okay? What about the anion of this? How about this guy? I'll give you a hint there. It's never been made before. Why? It's anti-aromatic, very unstable. Okay, just like Cyclo Butadiene. So this one, no. This has the 4 pi electrons. Okay, so we don't have any reactions to do that one. All right, let's do a couple bigger ones now. How about this here? Oop. Should have drawn these on the overhead. Ah, that's a really big one. It's in the aniline class of compounds. It has 14 carbons in it. It's called 14 aniline. How many pi electrons? Count them all up, 14 electrons. I'll give you a little bit on the NMR. These signals show up at 7.3 ppm. So what do you think? Aromatic or not? 14 pi electrons, does that fit the Huckel rule? Yes, where N equals what, 4? Or no, 3, sorry. N equals 3, so I'd be at 12 plus 2, yep, 14 pi electrons. It is flat, those are all fine there, but these hydrogens here in the middle, guess where they show up at? Now remember the induced ring current here is anisotropic, so on the periphery, they're shifted downfield, but on the interior here, you're actually subtracting from the external magnetic field. And these guys here in the middle resonate at 0 ppm. Wow, that's kind of an amazing thing. So it depends on how you're oriented to the magnetic field there. So that's a neat one to point out. What about this one? So this is 10 aniline, I think. If I can draw it. There you go. So there's hydrogen here and here. So this is 10 aniline, it's called. And how many pi electrons? 1, 2, 3, 4, 5, 6, 7, 8, 10. Okay, yeah, the name fits there. Is that 4n plus 2? Yeah, where n would be 2, right? Yeah, 8 plus 2 would be 10. Ah, but look, these 2 hydrogens here, and this is a smaller ring now, right, being 10 here. And these are pointing right at each other, and one is actually puckered up there, and one across here is actually puckered down. Sterically, it doesn't allow it to get fully planar. And guess what here? These hydrogens in the NMR around the periphery here are 5.8 ppm. So what do you think? Is 10 aniline aromatic or not? No, we would call it non-aromatic. It's more like a simple conjugated alkene system because it can't get aromatic due to the steric effect there in the middle. But it's a big enough ring, that'll be fine. Okay, what about this guy? How about some of these bicyclic aromatic? How about that one? Remember there's a common name for that, it's called naphthalene. And you could look at this ring separately. There's 6 pi electrons there, 6 pi electrons there. Or you can look at the whole molecule. How many total? 10 pi electrons. And it is flat, okay? So this is fused directly here, so definitely aromatic. Okay, 10 electrons. You can look at each ring individually. If you do resonance structures here, there's kind of a strange effect that you can begin to see. How about this resonance structure for it? Which resonance structure would be better for naphthalene? So I just rotated the electrons around here, right? And let's see, this one, yeah, has the 6 pi electrons here. What about that one? Here we're drawing this as a single bond for this resonance structure. But look, around the periphery here, we still have the 10 pi electrons. So this one's still aromatic. This one has extra aromaticity because both rings within the structure are aromatic, okay? So the book discusses a little bit about that. I'm not going to get into that too much. There are some resonance structures that are more important than others, and there you should maximize each small ring as being aromatic if you can, okay? You can do the example for anthracene and phenanthrene. There's a couple homework problems like that. So this is still aromatic, okay? Naphthalene is aromatic, definitely, flat and everything. 6 in each there, and 10 around the periphery, and 6 for this one, okay? So that's a little bit tricky thing, but the flatness and then the NMR, definitely in the 7 range, all of those. So yeah, that holds out okay there. Okay, polycyclics, we can go. Oh, let's do the heterocyclic ones first. I think this is an important topic to get into. So it's not just, the charge or the number of carbons. You can have heterocycles involved. So is pyridine aromatic? Okay. Is Parola aromatic? And these are a couple of heterocycles you need to know the name, okay, and the structure, be able to go between the structure and the name. Parola and pyridine, aromatic or not? Yes, okay, they're aromatic. Or we wouldn't be talking about them maybe. Or we see some variations where they're not aromatic, but what can we point to here? Well, 1, 2, 3, 4, 5, 6 pi electrons, okay? Yeah, it's just like benzene. In fact, if you look in the NMR, these signals are all in the 7 range, okay? What else is on nitrogen here though? Oh, lone pair. Do we need to worry about that right now? No. What's the hybridization of nitrogen though? We should worry about it enough to that point. Hybridization of nitrogen, what? It's got 1, 2, 3 things on it. So what is it hybridized as? sp2, right? Okay. We got the p atomic orbital here. We'll need to draw out the structure of it in 3D to get a better view of it. But this lone pair here is sp2 hybridized. It's on the periphery of the molecule. You can see the 6 pi electrons are involved here that are drawn there. So definitely it's Huckel okay. Let's look at it kind of flat here where we can see it and draw all the p atomic orbitals. And yeah, that's where the 6 pi electrons are, the aromatic effect. And so where is the lone pair here? It's right there. And you see it's perpendicular to this, right? So that's not involved in the aromatic counting. We don't count that. We count those 1, 2, 3, 4, 5, 6 to make it aromatic. Now it's a little bit different than Parola. So you got to follow me on this. What about this lone pair here now? Okay. Now, I already told you the bottom line. Parola is aromatic. So do we count that lone pair now or not? Yes, we need to count it because this is only 4 here, and that is the 6th one. So here's our sp2 hybridized bond here, sigma bond to this hydrogen on the periphery. This is in a p atomic orbital, part of the aromatic hextet, we say. Let's look at the structure Parola and verify that, okay? So kind of on the side here, let's see. Got the lone pair there. Okay, and there's the aromatic grouping, and you see the perpendicular sp2 bond to the hydrogen there is perpendicular to the p atomic orbital. P atomic orbitals are always perpendicular to things. That's what the p stands for. But here we have it part of the aromatic grouping. It's conjugated, we say there. We've got the 6 pi electrons, and indeed these resonate in the 7 range for Parola. So both aromatic. This is very typical here. We'll call these pyridine lone pairs versus Parola lone pairs, okay? Pyridine lone pairs, you don't count them. Parola lone pairs, you do count them, okay? You need to see that. And that's kind of evident from the Lewis dot structure. When we draw the thing and you see a double bond to nitrogen, that means the lone pair is going to be what? Not counted. Whereas we have single bonds drawn to the nitrogen in a heterocycle, whatever. Then the lone pair will be counted, okay? But you need to count them up and see how it will add to the structure there. So yeah, those are a good couple ones to keep track of. Pyridine and Parola. Let's look at imidazole here real quick. How about imidazole? And we're talking about it, so it's probably aromatic, right? Well, let's see how it's aromatic and try to analyze it. And we draw on all the dots there. And this is the one in histidine amino acids, so it's important there. We got two nitrogens, we've got some pi bonds, we've got a pyridine type lone pair here, okay? And we've got a Parola type lone pair here. Which one is counted in the aromaticity? Right, the Parola one. 1, 2, 4, 5, 6. So this one is not. That's in the sp2 hybrid. Well, they're both sp2 hybridized, right? This is the sp2 lone pair. This is perpendicular. This is in the p orbital. Okay. Let's look at it sideways and see. Hopefully it'll shake out here a little better. Here we got that, and then we got the lone pair back there. And we got the hydrogen coming out there. There we go. There's some Friday artwork for you, right? So what do we got? Oh, there's the lone pair there. Double bond here, there's 2 electrons there. And then we got the 2 electrons here. So there's the double bonds we drew in the static structure, right? And here's the Parola lone pair. There's the pyridine lone pair on the back. So is it aromatic? Yes, okay. So definitely aromatic. And we could double check that in the X-ray structure or the NMR and see how that goes. But make sure you can handle the 3D arrangement of where things are at. Okay, what about purine? And this is in DNA. So in guanine and adenosine, if you've had a little structural biology already, these are the polycyclic base pairs on the side of the ribose or the deoxyribose, right? And we've got a couple different nitrogens here. Well, actually 4 nitrogens. Wow, okay. Got a lot of lone pairs floating around. Need to keep track of that. So that purine there, is that aromatic? Well, we can kind of see we've got 6 electrons around here. Yep, so we'd say that ring's aromatic. Lone pairs here and here are what? Pyridine-like lone pairs. So these are sp2 hybrids. We don't count those. They're perpendicular, right? Yeah, this ring here, double bond there, that's 4 electrons, and we count that one. This is a Parola-like lone pair, right? So there's the aromatic grouping. There's another lone pair here. This is the pyridine type lone pair. We don't count that one. And we could draw some resonance structures of that as well, right? These are fully delocalized. We could draw some things around the ring. So base pairs in DNA benefit from this aromatic stabilization. That's kind of important to keep track of. What about this one? Let's do a couple more here. A little bit harder. And when I say harder, you're going to have to analyze it a little more, maybe, let's say. How about this structure? Here's a pyran type structure. Is that aromatic or not? Well, it's got a CH2 up here. Hopefully my drawing is good enough to see. We got lone pairs here. 1, 2, 3, 4, 5, 6. That fits the Huckel rule, doesn't it? What's the violation here? It's not continuous, okay? Is there a way we could make pyran aromatic here? What would we have to do? Let's see if we could bring this lone pair in and then have this come out and have a hydride come off. We could actually react it with tropylium cation, have that hydrogen hydride with this pair of electrons come off, and look what we'd form. We'd form this guy. Now, is this aromatic? Is beryllium cation aromatic? Yes, it is. It's flat, it's charged. It's got the 6 pi electrons though, and it definitely is aromatic. What about this one? Here's pyrimidone, a ketone made from pyridine. Well, kind of like pyridine. Now this one's a little bit strange. This one you need to look at the aromatic character and maybe a resonance structure. And this is a key thing here. A compound, sometimes when it's first drawn, may not appear to be aromatic, or there might be some violations. But if we can draw a resonance structure easily enough, guess what? It can become aromatic. So let's see. This one on its own, you could say 1, 2, 3, 4, 5, 6. Well, how we handle the ketone up there? That's exo to the ring. We need 6 or 10 or 14 pi electrons in a continuous ring. How do we handle those? Well, do we count like one of them or two of them, or just pull them out completely? Maybe that might help us out. Let's pull them out completely and draw this resonance structure. And then you can see whether this pyrimidone would be aromatic or not. Does that look like it's aromatic now? Yes, we've got the 6 pi electrons here around the ring. And yeah, we've got some charges here. It's neutral overall still, but because we can draw a significant resonance structure where we clearly see the Huckel rules all obeyed here, we say that this molecule is aromatic, okay? But there are some tricky things there. What about this one? Quinone. Quinones are in biology, in the electron transport chain in the mitochondria. Maybe you've heard of quinone, quinone 10 or quinone Q or whatever the common name is for that now. What about this quinone? We have 2 ketones across here. Aromatic or not? What do we have to do there? Let's see, if we draw a resonance structure like that, what do we get to? We have O minus, we have a cation there. Can we get the 6 pi electrons? Well, you could say that, but this is exo to the ring. It all has to be within the ring and continuous. So definitely not aromatic here. We draw another resonance structure here, then we wind up with just 4 pi electrons in there, okay? So this structure as it's drawn here, what are we gonna conclude here? Non-aromatic, okay? But this is a little tricky case. In fact, you can see in the NMR, the Proton Nmr, these guys on the side are in the 5 range. Okay, one other I want to point out, and then we'll go back to the overheads, and it's this one here. This is called azulene. And azul, what does azul mean in Spanish? It means blue, right? This is azulene. It's actually a blue compound. It absorbs down in the visible range. It's actually quite a polar compound too. It's freely soluble in things like ethanol and acetone, and it gives those solutions a blue color. Kind of a cool compound. Can we use Huckel theory to figure this structure out? Let's see, what could we do here? The whole ring around the periphery is what? How many electrons? 10 electrons. And you might think, right there, flat, continuous, yeah, it is aromatic, but what about this polarity effect? Let me tell you, this end of the molecule is partially negatively charged. This end is partially positively charged. Can we use Huckel theory or resonance effects to explain this now? I think it's one of the problems at the end of the chapter. I've put this on tests before. I don't know how I'd word it. There's different ways to word questions, right? But azulene, can we rationalize this partial negative, partial positive charge? Yeah, let's do this. Let's put these electrons right here. And let's just draw that resonance structure. We'll draw a couple more here, but let's see, what would that one look like? We'd have negative charge right here, and we'd have what? Positive charge right here. Now that doesn't seem like much, but let's draw this resonance structure. And let's put these electrons here and put these electrons out here. Now you'll actually see it, I think. Let's see what it looks like. We've got the 5-membered ring here. We'd have this here, negative charge. 3, 4, 5, 6. And we have plus charge here, here, and here. Okay. Now, what do we see? We see we've got this plus charge here. 1, 2, 3, 4, 5, 6 pi electrons. We might need to change our resonance structure here. But here you see 1, 2, 3, 4, 5, 6. This looks like the Cyclo Cyclopentadienyl Anion, right? Let's draw one other resonance structure here. Let's see, which one should we do? How should I do this? How about like this? Yeah, okay, let's do that one. I always have to experiment with it. And remember when you work these problems, you know, use your paper and try different things with it. And let's see. Yeah, we still have the cation there. We're good. Okay. Let's look at the two rings individually now. We have the charge separation, right? We have a cation here. That looks a lot like tropylium cation, doesn't it? And this looks like CP, Cyclopentadienyl Anion. In fact, let's redraw it like this. Negative, positive. Oh, I need another carbon in there. Okay, that's what it's equal to, right? One end's partially positive, and that gives it the aromatic character here for this ring. And this side has the aromatic anion character there. But the structure itself is aromatic overall, 10, right? But these are the individual rings, you could say, that give it that character. Anyway, that's azulene. I think it's an interesting example. Let's go back to the overheads here, and we'll wrap up with frost circles and a couple other things. Back to the full page view. There's our molecular orbitals of benzene. Like I said, those show up a lot better on CHEM352, and you can manipulate these and see all 6 of them. And remind yourself, the lowest one shown here has no nodes in the perpendicular plane. It has one big node right through the middle of the molecule, right? Through the node of the p atomic orbitals. There's always a node there. But through the ring here, crosswise, there's no nodes, right? That's when you get to psi 2 and 3. Remember, those are the wave function designations. So this is pictorial quantum mechanics, which often answers most of the questions we need to talk about. And as you introduce more nodes, you go up in energy, okay? And here's one molecular orbital, and then 2 more. Remember, only 2 electrons per molecular orbital, per any orbital. That's the Pauli exclusion principle of quantum mechanics. Spin paired, you don't need to worry about that. But there's a gap between the filled orbitals and the antibonding empty orbitals. So this is the HOMO position, and this is the LUMO position as we talk about that. And there's those depictions again. Again, go to CHEM352 to see that better. We can also analyze this with frost circles. Frost was a physical chemist, came up with this means of analyzing these things in the 1950s, and it has to do with inscribing a polygon that approximates the structure you're interested in inside of a circle. Hence the term frost circle, okay? And what that means is this polygon with the tip at the bottom of the circle here. So this is for Cyclo Propene one. You can see the 2 orbitals here are at the corners of the polygon, and then the bottom apex down here at the bottom is the one that has the 2 filled orbitals in it. And you see the halfway point, and these 2 unfilled orbitals are near the difference between the HOMO and the LUMO. And what this says in frost circle analysis, if the empty orbitals are near this halfway point and they're empty, it will be anti-aromatic. I'm sorry. That's right here for this one. This one is aromatic, where the filled one is below enough, this halfway point drawn through the diagonal position of the circle. I think I got that right, Aaron. Is that right? Okay. And the empty ones are far enough above it, and you fill everything below that diagonal point, then it is aromatic. Yeah, so this one's aromatic. We talked about that. That's 2 pi electrons, right? Flat, planar, continuous. Let's look at Cyclo Butadiene. Again, you inscribe it, the polygon, put the apex at the bottom here, and then you see the 2 next orbitals up are right at that division point, right at the diagonal point. And that's where Frost says, well, if you're starting to fill there, you're anti-aromatic. Okay, so I got ahead of myself there. Anti-aromatic, and it has to be constrained to be planar in order to have an anti-aromatic designation. And that means it's much, much higher in energy. And that's been borne out with theory. And I showed you how attempts were made to make that molecule. And then we got Cyclopentadienyl Anion. It is aromatic. Here's the inscribed polygon with the apex. And then the 2 points here you see are below the diameter. So you can fill in the 6 pi electrons right there. And there you're getting a feel for it, right? 2, 6. That's because you got the apex down here at the bottom, right? So it'll always be 2, 6, 10, 14 on up, 18, not 4, 8, 12. So it comes out of the quantum mechanics. Here's benzene that we've done before. I'm not drawing the circle there. You can see we're filling here. The corners here is where the MOs will be. 6 pi electrons aromatic. Here's tropylium cation with the apex at the bottom, and then the 2 here filled with the 6 pi electron. So yeah, this goes through it. You can see my graphic. All these graphics are on Learning Suite, right? My overheads for each chapter. And what does this look like? Who's this guy on the right? Right. Okay. David O. McKay, and he found this stone carved in Scotland on his mission. And this is this magic square here. And here we've got these polygons that we're learning about to be magical. And any 3 in a row here all add up to 18. So this is kind of neat. You've got the 2-membered ring here, which kind of looks like a ethylene, right? So you can add them up here, right? 6, 3, 9, and then what's this one? That's 9. This is cyclononane, right? So I don't think the stone carver 200 years ago had cycloalkanes in mind or aromaticity, but it's kind of fun to look through this, and I don't know. But yeah, that's just meant for entertainment value. Here's back to some real molecules here. This is some data gathered years ago by mass spec. And this mass spec data came out of acetylene, which is C2H2, right? Acetylene arc welding. And if you condense that material coming out, you can get graphite, or you can take graphite itself, which is, a lot of benzenes fused together, and react it in a high energy laser with high energy light, or an electric arc welding. Any arc welders out there? Probably acetylene welders are out there. Very high energy flame, very high energy stuff. But they noticed when they collected this material here and did a mass spec, there was always this peak right here for C60, which is 60 carbons. It comes out to a molecular weight of what, 720 then, adding that up? So what is that big peak? What's all this stuff coming out here? Well, it took them a while to figure it out, but it turns out to be buckyball. Buckminster fullerene is the name they gave it for Buckminster Fuller, who was an architect in the 50s and 60s, who made these geodesic dome type buildings. You see some of these around the country, but it's actually technically called a truncated icosahedron. And an icosahedron has 12 sides to it. If you truncate the icosahedron and clip off a corner of it, you get the 20 faces here. And it's a soccer ball, right? You have the alternating 6-member rings, 5-membered rings. And it's sp2 hybridized carbon, you could say. There it is. It looks like benzene, right? But is it flat? Let's see, it's spherical sp2 hybridized carbon, right? It is a soccer ball. Here's an icosahedron, which is 12 regular triangles. If you clip off the corners, there's where you get the 5-membered rings. Anyway, it took a mathematician at Houston University to help out Smalley. Croto and Smalley were the people who won the Nobel Prize. They were just puzzled by their mass spec. They had to go over to the math department and figure out the patterns here. They also have a C70 in it, which kind of looks like a football. There's C32, C50, and these bigger analogs. They look like chicken wire, don't they? If you flatten that out completely, of course, you have graphite, where they're all 6-membered rings. But this opened up a whole new area of materials. You can make these Bucky tubes that aren't completely spherical. They're kind of tubular, hollow-shaped. Different ways to adjust the conditions here to make tubes or shells. They're kind of geodesic domes inside of each other, which is kind of cool. And you can fill different things in there. I think this is some iron particles inside, or is it gold? It might be gold. I think gold nanoparticles are one of the first ones they did. Jelly-filled donut structures. There you go. There's a term for you. Good nomenclature. These are, of course, different allotropes of carbon. We say, what's an allotrope? That's where it's a material. It's just made up of one element. There are different types of it for carbon. We used to think that graphite and diamond were the only types, but now we have graphene. We can pull off a single layer off graphite and have a single layer material. Some people won the Nobel Prize for that more recently. And then these fullerenes, these cyclic spherical or tubular structures, is Kroto and Smalley. So it's 2 Nobel Prizes recently shown here. And diamond, of course, is one of the original ones. This is a gem material mined out of the ground, and it's all what? sp3 hybridized. You see the 6-membered rings, the cyclohexanes going in 3 dimensions here. Very stable, strong material. But can you burn diamond? Can you react it with oxygen and make CO2 and water? Yes, you can. It takes quite high temperature, and you have to crush the diamond up and get a high surface area. But diamonds are not forever. You can actually burn them. But yeah. Now, stay tuned for Chapter 18. That's what we're going on to next week on Monday. That'll be the 5 new reactions. Electrophilic aromatic substitution. Make sure you're reading ahead. We'll do nitration, sulfonation, halogenation, alkylation, and acylation. Okay? Those are the 5 new reactions. We saw no new reactions in Chapter 17. Yay! It was just the structure. Make sure you can analyze that and apply the Huckel rule and identify whether it's aromatic or non-aromatic, and then be reading ahead into Chapter 18. So very good. I think we are, no, there was one other thing I wanted to show you. Sorry. And that's this. Okay, application. Benzopyrene. This comes out of tobacco smoke. This is, the pyrene structure is just with the 4 here. And the extra benzene is called benzopyrene. And this comes out of soot. In fact, any organic material that you burn makes soot. It's kind of a black appearing stuff. Your barbecue is filled with this stuff, okay? It's not a good idea to inhale any organic thing that's on fire. About 20 nanograms comes out of a single cigarette. That's not very much, but if you smoke a lot or inhale a lot of burning campfires or whatever, you'll get some of this in your blood. And in the liver, this will be converted into this epoxide. Your liver does some oxidations with CP enzymes and oxygen. And this epoxide right here is electrophilic. It can be opened up with water to form the diol. Now it's more water soluble. It persists in the body a little longer. And this can be further oxidized in the liver to this epoxy diol. And this is the one that's known to intercalate into DNA and actually get alkylated by one of the amino groups on the base pairs. Okay, I think the guanine N7 amino group is the most nucleophilic one. There it is right there. That's opening up this epoxide right here and intercalating right there. Now, normally if that happens in a cell, it will kill the cell. It's very cytotoxic to cells. But if it mutates in the gene region of this protein called P53, now that's a tumor suppressor protein, or proto-oncogene. And if it gets mutated in the 3 hotspots here, and so this is arginine to histidine, arginine to Q, which is, which amino acid is that? We'll have to look at that later on, arginine to histidine. And if these 3 specific amino acids get mutated, then this is the mutated form of P53. It loses its ability to bind DNA, and that leads to uncontrolled cell division. And that's a hallmark of what disease? Cancer, correct. This is the most well-established molecular mechanistic pathway to a disease, the etiology of cancer, you can say. And it's through these electrophilic benzopyrene epoxides that lead to these specific mutations. Now, it kind of happens by chance, but if enough of those get mutated in those specific spots, then those cells can form a tumor and lead to a cancer. So lung cancer, for example, is well known that these P53 mutations lead to those mutations. And this is a frame shift mutation, if you remember any molecular biology. When this is read by the transcriptase, whatever, it leads to a different form of P53 that does not bind DNA very well. In order for it to suppress DNA replication and keep the cell from becoming oncogenic or cancerous, P53, the normal part, is bound to DNA and keeps it regulated. If the cell becomes mutated form of P53, then it leads to uncontrolled cell division. It rapidly divides and leads to a tumor. Anyway, that's kind of the take-home message there. Now, I throw those in now and then to just show this aromatic compound right here, aromaticity. Notice all these intermediates are still aromatic, can interact with these aromatic side chains on DNA. I know a little bit about the biology of it, but not all of it. Okay, this is just an application problem. I throw in a couple of these on each test, so know enough of those. If I talk about it in class and it's in your book, it's more likely I might discuss it, might have it on the final. Anyway, okay, very good. I think we're done here for Friday. We'll see you on Monday, going ahead into chapter 18. Very good. We'll see you then. Thank you.